Continuing on with the organic chemistry lecture series, today we're going to be discussing Chem 112, Chapter 2, which focuses on resonance, inductive effects, and acid-base chemistry. First and foremost, let's begin by discussing resonance structures. So a good introduction to this is to look at the acetate anion. The central idea behind resonance structures is that Lewis structures are often inadequate to describe the actual full structure of many molecules. For example, if we draw the Lewis structure for the acetate anion, which looks something like this, this is a perfectly valid Lewis structure for the acetate anion. But things start to run into complications when we start to have to answer questions such as, in this structure, which carbon-oxygen bond is stronger? Well, looking at the structure as we've drawn it, we would say that this double bond would be stronger. However, experimentally, both of the carbon-oxygen bonds have the same bond order, length, and strength. And this stems from the fact that in reality, those pi bond electrons are not localized at a single carbon-carbon bond. Instead, these pi electrons are spread across this pi system, and this electron density is evenly distributed across all atoms participating in the bond. So in terms of what we actually see, the actual structure for the acetate anion is closest to that of almost like a 1.5 order bond, where these pi electrons and that negative charge are distributed across this pi system. So when we look at this bond order, it's about a 1.5 bond. So part of the reason why we need to start to familiarize ourselves with resonance structures and use resonance structures in order to understand bond length and strength is because individual Lewis structures on their own are often inadequate to describe the actual bond length, strength, and bond order that we observe for many molecules. So, what are resonance structures? These are one or more valid Lewis structures with the same skeletal formula, same connectivity, but a different distribution of electrons in pi bonds and lone pairs. You can think of resonance structures as drawing multiple structures with varying distributions of electrons throughout a pi system. So for example, for acetate, one of the possible Lewis structures looks something like this. And we can draw an equally valid resonance structure where we redistribute our pi bonds and lone pairs to yield a resonance structure where instead of having a lone pair and negative charge on the bottom right oxygen, we have it on the topmost oxygen in our structure. I want to be clear that these are just depictions of our structure. The actual structure is more of an average of all the different resonance structures that we can draw. Now, one thing I do have to be very clear about, resonance is not rotation. And we can show this by trying to draw out some resonance structures where we've labeled one carbon and we check and see how the bonds change. For example, we can draw a valid resonance structure for the following. In this case, this is an allylic cation. We can redistribute our pi bond, and this in turn would give us the following valid resonance structure. Now, one way we can tell that we've clearly changed the distribution of pi bonds in our molecule is if we arbitrarily label one of the carbons. Suppose it's radio labeled in some way. Suppose it's a carbon 13 atom instead of just a normal carbon 12 atom. You can see that when we draw out our resonance structure, we see that there is now a new carbon-carbon double bond connected to this labeled carbon. So resonance structures aren't just rotating our molecule, we're looking at different distributions of electrons in our pi system. There's a different bonding arrangement in terms of our double bonds and a different distribution of our pi electrons. In terms of what actual structure we observe, the actual structure is a weighted average of all resonance structures based on their favorability. So for example, for the following cation, the actual structure, instead of having the double bond ascribed or assigned to any particular carbon, instead, those pi electrons are distributed across all three atoms in our pi system, as is the positive charge. We call this average structure the resonance hybrid. Okay, so let's talk about resonance and conjugation from the perspective of MO theory, molecular orbital theory. Pi bonds involve the overlap of unhybridized p orbitals perpendicular to the bond axis. So we have two p orbitals, they can overlap, and this yields a pi bond. We can extend this idea to what are known as pi systems, where pi bonds adjacent to parallel p orbitals can overlap and generate an extended pi bond called a pi system. A pi system is a set of adjacent parallel p orbitals or pi bonds. Importantly, in order for an atom to participate in conjugation, the atom needs an available p orbital and thus requires an sp2 or sp hybridization. sp3 atoms cannot participate in traditional pi systems and traditional conjugation. Why does this occur? What's the benefit of this? Well, the electron density is delocalized across the pi system, and this has some benefits in terms of stabilizing the electrons that are participating in the pi system. So for example here, if we have a pi bond and we have a p orbital, this p orbital is parallel to the pi bond, so we can overlap all of the p orbitals to generate a pi system. As a result of this, we can spread out our electron density across all atoms participating in this pi system and thus stabilize that electron density. The way that we represent these kinds of delocalized pi electrons is using dashed bonds. So for example, for ozone, rather than drawing out both the resonance structures, if we wanted to portray the actual structure, we'd use this dashed bond notation, which is essentially saying we're distributing electron density across these three oxygen atoms participating in the pi system. Conjugation, once again, is the overlap of parallel p orbitals in three or more adjacent atoms to form a continuous extended pi system. Let's look at a case study here. In this case, we're going to want to draw the pi bonds and p orbitals overlapping in the following cation. And then we're going to answer the question, how many pi electrons are present in this system? So first and foremost, this carbocation has an sp2 hybridization. How can we tell? We have 1, 2, 3 bonded atoms, and thus to form the required 3 sigma bonds, this carbon adopts an sp2 hybridization. Likewise, this carbon on the right will also adopt an sp2 hybridization. This carbon here is also sp2, and we have a pi bond between these two carbons. So then I'm going to draw out my three carbon atoms. This carbon, as it's sp2 hybridized, has an available p orbital. I'm just drawing the hydrogens here as H's just for simplicity's sake. The central carbon also has a p orbital, as does the carbon on the right. However, these two carbons are sharing electron density via a pi bond. These p orbitals are overlapping to form a pi bond. This carbon on the left, it has a lot of positively charged character. It's a carbocation. Now, given that we have a p orbital that is parallel to a pi bond, we can overlap our parallel p orbitals to form a pi system. So in this case, we're distributing the electron density found in this pi bond across all of our atoms, and we're distributing our positive charge across all of our carbon atoms. Importantly, if we're counting pi electrons here, we have one pi bond, and this one pi bond represents two pi electrons. Remember, two electrons per bond. We only care about the pi electrons because it's those pi electrons and electrons held in our conjugated p orbitals that are distributed across our pi system. The single bonding electrons we don't particularly care about for this exercise. So in this case, in our pi system, we have two pi electrons. How did we get that number? We have one pi bond and nothing much else participating in terms of sources of electron density in our pi system, and that pi bond has two pi electrons. Why do we care about this? Well, it's important to be able to count pi electrons as it tells us a little bit about the reactivity and behavior of our pi system, of our conjugated system. This is going to be very important later on. So let's continue on discussing pi systems in the context of molecular orbital theory. We're going to look at ozone and the allyl anion as some case studies. Just like before, when we combine and overlap p orbitals, we generate what are known as molecular orbitals equal to the number of conjugate orbitals combined. Our general rule where the number of orbitals that we put in equal the number of molecular orbitals that we get out. Importantly, as part of conservation of energy, for each bonding molecular orbital we generate, an antibonding molecular orbital is generated. Something interesting happens if we have an odd number of combined orbitals. We generate what's known as a non-bonding molecular orbital. As its name implies, in a non-bonding molecular orbital, you're often going to see lone pairs or other sources of electron density isolated and generally localized on one or more atoms in our structure. Okay. In general, one thing that happens is pretty interesting when we look at these conjugated pi systems and when we look at these molecular orbitals for conjugated systems is that as orbital energy increases, the number of nodes increases by one, starting from 0 nodes. So as you go up and up in terms of energy, your number of nodes increases by one. What is a node? As we discussed, a node is a region with no electron density. And generally, nodes are placed symmetrically on or between atoms. So for example, in this case, we have a node here in the following molecular orbital picture. And a key signpost for a node is that on either side of the node, you have regions of opposite phase. Remember, p orbitals are phased with regions of positive and negative amplitude, not charge, amplitude. And generally, when you have a node, across that node, you'll see regions of opposite phase, which makes sense because you cannot overlap regions of opposite phase constructively. So let's do some practice here and let's try to draw some molecular orbital pictures for butadiene. And let's draw a molecular orbital diagram for a molecular orbital with one node and two nodes. So first, for one node, because nodes are distributed symmetrically, I'm just going to cut my molecule in half. On one side, I'm going to draw regions where the phasing is the same. And then across the node, we're going to draw regions of opposite phase. So to clarify, every time you look across a node, you're going to see that the phasing is opposite across the node. So as you can see, in the case where we have one node, we have one side where we have overlapping regions of the same phase. We hit the node, and now on the other side of the node, we see that the phasing is opposite. This makes sense. A node is a region with no electron density, and you generally see a node when you have p orbitals of opposite phase on each side of the node. Okay, now let's look at what happens when we have two nodes. So we want to split this molecule and place the nodes as symmetrically as possible. So we'll place a node here and here. From here, we're going to draw our first set, and we'll put the phasing where the positive amplitude is going to be on the top. You can do it either way. We cross a node, we have the opposite phase on the other side of the node. And then finally, we cross the other node. We have it the opposite phase on the other side of the node. One thing that you can take away from this is part of the reason why the orbital energy increases as we increase the number of nodes is that we have less constructive orbital overlap. And as a result, the electron density in that molecular orbital is less stable compared to if we had fully constructive overlap. Now, why is it important that we know how to draw these molecular orbital pictures for conjugated systems? Well, it allows us to better understand the overall energy and the overall patterns of reactivity for conjugated systems. So for example, for ozone, we drew out molecular orbital diagrams with 0, 1, and 2 nodes arranged in order of increasing energy. As you increase the number of nodes, the orbital energy increases. We then take our pi electrons, in which case we have 2, 4 pi electrons, and that's why when we fill our molecular orbital diagram, we fill it with 4 electrons in total. We're taking our molecular orbital diagram and filling it with our pi electrons. Let's repeat this process, and this time we're going to look at the allyl anion. Here we see we have 2, 4 pi electrons, 2 from the pi bond, another 2 from the lone pair. So if we're filling this diagram, we'd fill it with 2, 4 electrons. So as you can see, the highest energy occupied molecular orbital has electron density in the non-bonding molecular orbital. The way that we can interpret this in more of a physical sense is looking at this allyl anion. You typically see electron density in non-bonding molecular orbitals when you're dealing with these kinds of conjugated anions. I'd like you to take a few moments and try to fill out the molecular orbital diagram for the allyl cation and allyl radical. Keeping in mind we need to count the pi electrons, and then we fill our molecular orbital diagram with those pi electrons. So I'd like you to pause the video, work through that, and we'll discuss momentarily. Okay, so in this case, for the allyl cation, we have two pi electrons, so we fill our diagram with our two pi electrons. For the allyl radical, we have two, three pi electrons, two from the pi bond, one from the radical. So we fill our diagram with one, two, three pi electrons. Radicals are not especially stable, given that they have this unpaired electron, and generally they're pretty keen to participate in reactions such to either donate that unpaired electron or abstract an electron from another molecule. Okay, let's talk now about how to draw resonance structures in a systematic way. And let's talk about arrow pushing. This is an important skill that you'll need, as we'll use this same concept when drawing reaction mechanisms. So, in terms of arrow pushing steps to draw resonance structures, we can move electrons shared in pi bonds to any atom participating in the pi bond. For example, if we have a carbon-phosphorus double bond, we can push the electron density in this pi bond onto carbon. And in turn, when we break this pi bond, we draw an arrow from the pi bond to the atom receiving the lone pair. So as you can see, we went from a carbon-phosphorus double bond, a pi bond. We pushed the electron density from this pi bond onto carbon, and thus we end up with a lone pair on carbon. You may say, why did we choose carbon? Generally, when you're breaking a pi bond and placing a lone pair on one of the atoms participating in the pi bond, you're going to want to put the lone pair on the most electronegative atom. In this case, that would be carbon. Let's practice this skill. So here we have formaldehyde. Let's draw a resonance structure. So we have a double bond, we have a pi bond, and we can take those pi bonding electrons and distribute it to one of the atoms participating in the pi bond. Given oxygen's way more electronegative, we're going to push those pi electrons onto the oxygen atom, and that gives us an additional lone pair. This additional lone pair has consequences. The formal charge of oxygen now becomes -1. Likewise, carbon, as it lost a bond, has a positive formal charge. So just make sure when you redistribute your pi electrons, you recalculate formal charges. Okay, now another trick that we can do involving arrow pushing is if a lone pair is adjacent to a carbocation, which is a carbon with a positive charge, we can form a pi bond using that lone pair. To form a pi bond, you draw an arrow from the lone pair to the bond that you want to form between atoms. So I'm going to take my lone pair, draw an arrow, and I'm going to form a new pi bond. This in turn generates a sulfur carbon double bond, and we lose a lone pair. And as a result, the carbon is no longer a carbocation, it has a formal charge of 0. Let's just prove that. 4 minus 4 bonds gives us a formal charge of 0. By the same token, if we have this amine adjacent to a carbocation, we can kick a lone pair down, generating a double bond. And this time, I'd like you to note that the nitrogen picks up a positive formal charge. Now, if a pi bond is adjacent to a carbocation, we can also form a new pi bond. To form a pi bond, you draw an arrow from the pi bond to the new bond that you want to form between the two atoms. Generally, you're trying to form a bond with the atom containing the carbocation. For example, I can take this pi bond and redistribute it to generate a new pi bond and a new carbocation. One thing to be very careful about is to make sure that you are only redistributing pi electrons. Resonance structures do not break sigma bonds. So let's practice this with another example. So in this case, we have a carbocation here and a pi bond adjacent. So we can redistribute our pi bond to generate a new double bond, a new pi bond, and a new carbocation. For those wondering, what about the geometry of that pi bond? You can draw either geometry. This this double bond can be either cis or trans. One last common manipulation that you can do to draw valid resonance structures is if a lone pair is adjacent to a pi bond, we can generate a new pi bond and a new lone pair. So in this case, you draw an arrow from the lone pair to the single bond between two atoms, and then you draw a second arrow from the pi bond to the atom without the lone pair. So for example, in this case, nitrogen can kick its lone pair down to form a pi bond. This breaks the adjacent pi bond and generates a new lone pair. Let's practice this. In this case now, if we have a lone pair adjacent to a pi bond, such as in this allyl anion, we can push this lone pair down to make a new pi bond and break our original pi bond to generate a new lone pair. Okay, so we've discussed the common arrow pushing steps to draw valid resonance structures. Let's talk now about a special subclass of compounds known as aromatic compounds and how to draw resonance structures for aromatic compounds. So a set of fully conjugated pi bonds in a ring are known as aromatic or anti-aromatic systems. Aromatic rings have 4n plus 2 pi electrons, 2, 6, 10, 14 pi electrons, and aromatic rings are very stable. As a counterpoint, anti-aromatic rings have 4n pi electrons, 4, 8, 12 pi electrons, for example, and anti-aromatic rings are not particularly stable. So for example, if we look at benzene, for example, we have 2, 4, 6 pi electrons, and we have a set of fully conjugated pi bonds in a ring. For an anti-aromatic example, we have, in this case, cyclobutadiene. And in this case, we have 2, 4 pi electrons, so this would be anti-aromatic. Now, when drawing resonance structures for these types of aromatic and anti-aromatic systems, the pi bonds can be moved to the adjacent bond, clockwise or counterclockwise, to give a new valid resonance structure. You want to draw an arrow from each pi bond to the adjacent sigma bond. So in this case, for benzene, we can push our pi bonds clockwise one carbon over, and that generates the following equally valid resonance structure. One thing to note is when drawing resonance structures, you use these double-headed arrows and you put your resonance structure in brackets. Give an attempt to draw a resonance structure for this cyclobutadiene compound, and I'll give you a few moments to do that. So in this case again, we push our pi electrons one carbon over to generate a new set of pi bonds. And this is a valid resonance structure for this compound. Let's do some practice now. I'll do the first two, you'll do the next two. In this case, we're asked to draw a valid resonance structure for each molecule and label each as aromatic or anti-aromatic. So this is cyclooctatetrene. So we have 2, 4, 6, 8 pi electrons. So this would be anti-aromatic. We can take our pi electrons and push them over one carbon to generate a new set of pi bonds. This in turn gives us the following valid resonance structure. Almost looks like a stop sign. Okay, let's look at this next case. In this case, this is pyrrole. In this case, we have 2, 4, 6 pi electrons. Remember, this nitrogen is sp2. So in this case, this is an aromatic compound. And we can draw a resonance structure by pushing a lone pair down. That in turn displaces our pi bond, which in turn generates a lone pair. Rather than pushing it throughout the pi system, I'm just going to push it one carbon over. So the lone pair kicks down, we get a new pi bond, the original pi bond breaks, and we get a new lone pair. Now, is this resonance structure particularly major? No, but we can draw a resonance structure for this molecule. Okay, let's look at another two examples. So this time I'd like you to pause the video and work through these two examples, and we'll discuss them momentarily. Okay, so in this case, we have 2 pi electrons. So this would be an aromatic compound. We can push our pi bond over in order to generate a new pi bond and a new carbocation. Looking at this next molecule, before we do anything, let's draw a resonance structure. So I'm going to take this carbonyl and I'm going to redistribute it those pi bond electrons up to the oxygen atom. From here, we can see something pretty interesting. We have 2, 4, 6, so we have 6 pi electrons. This would be an aromatic compound, or at least this compound has a lot of aromatic character. You can take this one step further and redistribute the pi bonds throughout this pi system to generate another valid resonance structure. Generally, for these aromatic compounds, you can draw a fair number of valid resonance structures. Okay, let's keep going now, and let's talk a little bit about favorable resonance structures and the resonance hybrid. So, how do we determine which structure is a major or minor contributor to the overall resonance structure? How do we go about gauging contribution of each structure? Well, to do this, we're going to talk a little bit about some rules regarding favorable resonance structures. The actual structure that we observe in terms of bond length strength is the weighted average of all resonance structures based on their favorability. Favorable resonance structures that are major contributors satisfy the octet rule for second row elements, minimize formal charges, and they place negative formal charges on electronegative atoms and positive formal charges on less electronegative atoms. So let's look at some examples. So here for the following anion, which is known as an enolate, you can take your your lone pair, push it down to generate a new pi bond and a new lone pair. If we compare these two resonance structures, we can either have a negative charge on carbon or oxygen. Given oxygen is far more electronegative, the resonance structure on the right would be major, or at least more favored. Likewise, if we look at an amide, when we redistribute our electron density in our pi system by pushing down this lone pair to make a pi bond and breaking the previous pi bond to generate a new lone pair, we have two possible resonance structures. Both of these structures fulfill the octet rule. The first structure is going to be most major, but this second structure is not bad. It fulfills the octet rule, places negative charges on electronegative atoms, and the formal charges aren't particularly large. So part of the reason why it's important to be able to gauge the contributions of different resonance structures to the actual structure is they can give a lot of insight into patterns of reactivity and explain patterns in terms of bond length and strength. So for example, let's look at some cases where we draw some resonance structures for each compound and identify the most major resonance structure. So here I have a pi bond and a lone pair. I'm going to start by just kicking up this pi bond and generating a lone pair on oxygen. Now, given the fact that this structure does not follow the octet rule, it's not going to be particularly major. But the reason why I'm drawing it is that if you're ever having trouble with multi-step arrow pushing, you can always break things down to the fundamental steps. So I'm going to kick this nitrogen lone pair down, and that in turn generates a nitrogen-centered cation and a new pi bond. We can then also redistribute our pi bond electrons by kicking down any one of our lone pairs adjacent to our pi bond and forming a new pi bond while breaking the original pi bond to generate a new lone pair. So there shouldn't be a lone pair there anymore. Perfect. And now we have a lone pair on this nitrogen. Okay, perfect. So in terms of the most major, it'll be this neutral structure on the far left. If I had to rank them in order, this structure will be the most major. These two structures that fulfill the octet rule but have non-zero formal charges would be the next. And this last structure would be extremely minor, in part because it doesn't fulfill the octet rule. I'd like you to try drawing out some resonance structures, this time for the following compound, and I'd like you to identify the most major resonance structure after drawing all of the reasonable resonance structures. So I'd like you to pause the video and work on that, and we'll discuss this momentarily. So, first things first, I have a carbocation adjacent to a pi bond, so I can kick my pi bond over, and that in turn generates a new pi bond and a new carbocation. From here, I have a carbocation next to a lone pair, so I can kick my lone pair down, and that in turn generates a structure that fulfills the octet rule. Now, in this case, only one of these structures fulfills the octet rule, so the structure on the far right will be major. These other two structures would be minor, and they're pretty close to one another. There's not really a huge distinguishing factor between these first two structures. Both of them do not fulfill the octet rule, and as such, that's why they're minor contributors. Okay, so we've spent a lot of time drawing resonance structures. Let's talk a little bit about the actual structure, the resonance hybrid. The actual structure we observe is a weighted average of all resonance structures based on their contributions. So for example, for the following anion, we can draw a resonance structure where we redistribute the pi electrons by kicking down this lone pair and breaking our pi bond. From here, if we think about the average bond order here, we have one structure with carbon-carbon double bond character and another structure where there's a carbon-carbon single bond and a carbon-oxygen double bond. So in reality, this carbon-carbon bond length is going to be closer to 1.5, the average across the major resonance contributors. While the carbon-oxygen bond order will also be close to 1.5, given that in the two major contributing structures, it has a bond order of 1 and 2, and the average of that is 1.5. So the actual structure we see in terms of bond length and bond order is the average of resonance contributors. It's not an exact mathematical expression. It's more an approximation because not all resonance contributors are equal contributors. One thing I'd also like you to note is that we have a negative charge that is distributed across these atoms in our pi bond. So it's not like the negative charge is highly localized on any one atom. So why is this important? Well, the resonance hybrid can help us understand bond order. The actual bond order is the weighted average of the bond order found in each resonance structure. To calculate the average bond order, draw the major contributing resonance structures, determine the bond order of a given bond in each structure, and then you take the average bond order for that bond across all structures. For example, looking at NO2 minus, which looks something like this. We can draw two valid resonance structures. Again, if you have a lone pair adjacent to a pi bond, you can push those pi electrons down to generate a new pi bond and a new lone pair. Now, let's take a look and let's focus on one bond in particular. Let's just focus on this bond here. So here, in one structure, it has a bond order of 2. In the second major resonance structure, it has a bond order of 1. So if we're drawing out our resonance hybrid, the average bond order across these two major contributing structures is 3/2, which is 1.5. So in reality, if we looked at the nitrogen-oxygen bond order, this bond order would be about 1.5. The same is true for the opposite nitrogen-oxygen bond with its average bond order as well of about 1.5. Okay, so with this example in mind, I'd like you to take a look at the following, which is the carbonate anion. I'm going to give you the original structure for the carbonate anion just to expedite this process. I'd like you to draw a few resonance structures, and I'd like you to tell me, focusing on this bond here, what's the bond order for that bond in the actual structure. So I'd like you to pause the video and work through this example, and then we'll discuss. So we can, in turn, redistribute our pi electrons by kicking a lone pair down and breaking the pi bond to generate a new lone pair. Again, part of the reason why we're not entertaining structures that do not fulfill the octet rule is they're likely not to be major contributors. Okay, we're now ready to do a tally of the bond order. Here the bond order is 1, here the bond order is 2, here the bond order is 1. 2 plus 1 plus 1 divided by 3 total contributing structures gives us about a 1.33 bond order. So what this tells us is in the actual structure, these bonds are not 1.5 bonds between carbon and oxygen. This bond order is closer to 1.33. So qualitatively, this carbon-oxygen bond is weaker than a traditional carbon-oxygen double bond, and it's only slightly stronger than a carbon-oxygen single bond. So the bond order can give you a sense of the relative bond length and strength. So let's do some case studies now. So in this case, we're asked to calculate which carbon-carbon bond is the strongest in the following structure and what is the carbon-carbon bond order. So in this case, we can draw some resonance structures for this benzene ring. We can push each of our pi bonds one carbon over, and that generates the following resonance structure. Doing a tally now of bond order, we have a bond order of 2 and 1. 2 plus 1 over 2 gives us a bond order of 1.5. And we can conclude, looking at each of these bonds, that all carbon-carbon bonds are equally strong. This is a pretty common characteristic of benzene and other aromatic rings, where in essence these pi electrons are spread across this aromatic pi system, and thus all of the carbon-carbon bonds have the same bond order. This next example requires you to tackle it with a little bit more nuance. I'd like you to pay special attention to the charges and think back to our structure contribution rules, where major structures prefer to place negative charges on electronegative atoms and positive charges on the least electronegative atom. With that hint in mind, I'd like you to tell me in the following two structures, which structure has the strongest carbon-oxygen double bond. So take a few moments to work on that. I would suggest pausing the video, and we'll discuss momentarily. Okay, so let's draw out our major contributing structures. We have a lone pair adjacent to a pi bond, so we can kick that lone pair down to generate a new pi bond and a new lone pair. These resonance structures that we're going to draw for these two compounds are, by their very definition, minor. Why are they minor? We have some non-zero formal charges, despite the fact we fulfill the octet rule. And where we're placing these formal charges is not particularly good. We have oxygen and bromine, some pretty electronegative atoms, and we're placing positive formal charges on those atoms. If we had to pick in terms of electronegativity and in terms of capacity to accommodate a positive charge, bromine, being a halogen, does not typically accommodate positive charge as well. Oxygen is not happy with this positive charge either, but bromine in particular and other halogens, it's generally quite rare to place positive formal charges on halogens in a major contributing resonance structure. So this contributor we would consider very minor, while this contributor would be minor but less so. Okay, so in this case, when we consider which structure has the strongest carbon-oxygen bond, the major resonance structure in each of these two cases has a bond order of 2. The more this minor structure with a bond order of 1 contributes, the weaker our carbon-oxygen bond will be. Because this structure with a positive charge on bromine is very minor, in turn, what this tells us is this carbon-oxygen bond in this structure here is going to be stronger. Why? Because it has less single bond character, because this resonance structure is a very minor contributor. So, this is a classic type of analysis where you look at the resonance contributors, and in this case, the resonance contributors have a lot of carbon-oxygen single bond character. The more they contribute, the weaker the carbon-oxygen bond in our actual structure will be. Because in this case, the structure with a double bond to bromine is a very minor contributor, our carbon-oxygen bond has way more double bond character than in this carboxylic acid, which is the structures on the left. So, this is why the rules for determining major and minor contributors are so important, as it can help us tease out minor differences in terms of bond length and strength. And we can observe these differences using techniques such as IR spectroscopy, and you'll see this idea again in future chapters. Let's also talk a little bit about the resonance hybrid and partial charge. Resonance structures provide information on the reactivity of atoms in our structure. We can use it to identify electron-rich or nucleophilic atoms, which are given this delta minus symbol, and electron-deficient or electrophilic atoms, which are given a delta plus symbol. To identify electron-rich and electron-deficient atoms, we examine the partial charge of each atom in all major contributing resonance structures. So for example, in this case, we have a negative charge on oxygen. We can draw a resonance structure that fulfills the octet rule, that in turn places a negative charge on carbon. What this is telling us is that carbon has electron density on it, and this carbon is relatively electron rich. Likewise, oxygen has a fair amount of electron density surrounding it, a fair amount of negative charge, and a partial negative charge. Likewise, for cations, we can draw a valid resonance structure for the following cation. And as we can see in our actual structure, each of these two carbon atoms have a positive charge in one or more of our major contributing resonance structures. And as such, in our actual structure, these two carbons have a large amount of electron deficient or partial positive character. We can use this same logic to help identify atoms that are electron rich and electron deficient in other structures. So I'd like you to pause at this time and work through these two examples, and then we'll discuss momentarily. Okay, so in this first case, we have a lone pair next to a pi bond. So we can redistribute our pi electrons by kicking the lone pair down, forming a new pi bond, and generating a new lone pair. This in turn gives us the following resonance structure. And this structure is a contributor, though it's not as major as our original structure. Why is this useful? Well, what this tells us is that the nitrogen has some partial positive character, very minor, but this carbon is very electron rich and has some nucleophilic character. This will be important later on when we try to determine patterns of reactivity. In many reactions, this carbon, as we can see in this contributing resonance structure, has a lot of electron density on it. And as a result, this carbon can act as a nucleophile. Looking at this next case, we have an oxygen with a negative charge. We can, in turn, kick the lone pair down to generate a new pi bond and a new lone pair. We can repeat this process once more, again generating a new pi bond and a new lone pair. Now, what does this tell us? This tells us that in these contributing resonance structures, the carbons at the alpha and gamma positions have a large amount of electron density, have a large amount of anionic character, and they have a buildup. And there is a large amount of partial negative charge character on these carbons. So in terms of reactivity, these carbons, which have negative charges in one or more of our contributing resonance structures, would be considered nucleophilic, electron-rich carbons. Let's look at an advanced example where we're going to draw some resonance structures for the following molecule. We're going to identify the major resonance structure or structures and identify all electron-rich atoms. I'd like you to pause the video at this time, and then we'll work through this example momentarily. Okay, so first and foremost, again, we have a lone pair next to a pi bond, so we can redistribute that lone pair to generate a new pi bond, and in turn, from here, we can take that same lone pair, push it down to generate a new pi bond and a new lone pair. I'm going to draw this structure upright just because it's a little faster for me to draw it that way. From here, we can take our lone pair and kick it down across the pi system to generate a new pi bond and a new lone pair. Okay, these are all of the major resonance structures that fulfill the octet rule. So, taking a tally here, if we wanted to identify atoms that are electron rich, we just have to look at each of our resonance structures and identify which atoms have a negative charge in one or more of the resonance structures. So we see this atom here has a negative charge in one of our contributing resonance structures, and this atom here, as well as both of the carbonyl oxygen atoms. So with that, we've drawn out multiple valid resonance structures and identified the electron-rich atoms in this molecule. Really powerful stuff. Okay, let's keep going now and let's talk a little bit about conjugation and resonance stabilization. So in general, conjugated pi systems are lower in energy and more stable than non-conjugated pi systems. This is evidenced via heat of hydrogenation, where stable, low-energy alkenes produce smaller heats of hydrogenation, which is the heat released upon reaction with hydrogen. For example, for butadiene, the conjugated diene is about 15 kilojoules lower in energy than the non-conjugated diene. We can attribute this difference in energy to the increased stability that the conjugated system has because it can delocalize its pi electrons across the entire set of atoms participating in the pi system. Let's talk a little bit about the MO theory explanation for the stability of conjugated systems. Bonding molecular orbitals are formed from overlapping p orbitals in a pi system. The bonding molecular orbitals formed from this overlap are lower in energy than an isolated pi bond. The more orbitals that we overlap, the lower in energy are bonding molecular orbitals, just as a virtue of conservation of energy. So for example, if we look at ethylene versus butadiene, the more p orbitals we have in conjugation, the lower in energy our bonding molecular orbitals are. Why is this? Well, pi bonding electrons are distributed over all conjugated atoms. And as such, the pi bonding electrons are stabilized by each of the atoms in conjugation. You can think of it as each of the atoms participating in the conjugated system contains a nucleus with a positive charge. Our negatively charged electron, because it can interact with more atoms, because it can be distributed across this pi system, is in turn stabilized by the nucleus of each atom participating in the pi system. Okay, we now have to talk about a very, very important idea, which is this idea of localized and delocalized lone pairs and resonance considerations when we talk about molecular geometry. So a localized lone pair is a lone pair that is not in a p orbital and thus cannot be delocalized across a pi system. This occurs in two cases. The first case, the lone pair is not held in a p orbital. This occurs in pyridine and nitrogen atoms with a bent trigonal planar geometry. For example, this nitrogen atom here has 1, 2 bonded atoms and a lone pair. It is sp2. When we think about this nitrogen, the lone pair is being held in an sp2 hybrid orbital. The nitrogen is using its p orbital to form its pi bond. Because this lone pair is held in an sp2 orbital and not in a p orbital, this is a localized lone pair. We cannot distribute this lone pair across the pi system because it's not in a p orbital. We call these nitrogens pyridine type nitrogens. The second case occurs when the lone pair is held in a cross-conjugated p orbital, where there's no possible orbital overlap. Looking at this azide compound, for example, we have a carbon-nitrogen pi bond, which is formed via the overlap using one of the nitrogen p orbitals. The second nitrogen p orbital is perpendicular to the first. And this is where our second pi bond is formed. The remaining nitrogen atom lone pair, one of which is held in a localized orbital, the other of which is held in a conjugated p orbital. Why is this important? What this is showing us is that depending on the orientation of our p orbitals, a given lone pair can only potentially be conjugated with part of the pi system. This is why it's important to be able to visualize orbital diagrams to get a sense of which p orbitals are parallel and which ones are perpendicular. We call this phenomena where you have pairs of perpendicular p orbitals cross conjugation. So we've talked about localized lone pairs, which generally occur when the lone pair is held in a hybrid orbital instead of a p orbital. What about delocalized lone pairs? Delocalized lone pairs occupy a p orbital parallel to a pi system. Delocalized lone pairs are stabilized as they are distributed across the pi system. So for example, this lone pair in an amide is delocalized. Why? This nitrogen will adopt an sp2 hybridization. Why would it do that? Well, in this case, if we have our carbon-oxygen bond, which I'm going to draw like so, we have a pi bond. This carbon is also connected to a CH3 group, and it's connected to a nitrogen atom. If this nitrogen adopts an sp2 hybridization, you can place your lone pair in a p orbital, and thus this lone pair can participate in conjugation to this pi system. And this conjugated delocalized lone pair is more stable. Now, this means we have to account for resonance effects on hybridization. So atoms with a lone pair adjacent to a pi system prefer to adopt an sp2 or sp hybridization in geometry so the lone pair can be stabilized through conjugation. This nitrogen prefers to adopt an sp2 hybridization in part because it allows us to place the nitrogen lone pair into a p orbital, and in turn, it allows that nitrogen lone pair to participate in conjugation. By the same token, this carbon with a lone pair adjacent to a pi bond or pi system prefers to adopt an sp2 hybridization. In part, so this carbon can place its lone pair in a p orbital, and thus the lone pair can participate in conjugation with the pi bond and pi system, which stabilizes the lone pair. So in general, when you have an atom with a lone pair adjacent to a pi bond or pi system, it'll prefer to adopt an sp2 hybridization or an sp hybridization if necessary, so that its lone pair can be placed in a p orbital and that lone pair can be delocalized across the pi system. Very important. Okay, let's do some case studies, regarding localized and delocalized lone pairs. So in this case, we're asked to predict whether each nitrogen lone pair will be localized or delocalized, and indicate the hybridization and predict the geometry of each nitrogen atom. So let's take a look now. Here we have a nitrogen that has 2 bonded atoms in a lone pair. It's sp2 and it has a pi bond. What this means is that this lone pair is being held in an sp2 hybrid orbital. So this lone pair is localized. You can say that this is a pyridine type nitrogen. By the same token, this nitrogen contains a lone pair. It is sp3 hybridized, but there's nowhere for this lone pair to be delocalized. So this is another example of a localized lone pair. For reference, this sp2 hybridized nitrogen here would be trigonal planar. while the sp3 nitrogen would be trigonal pyramidal. This final nitrogen, in this case, has 1, 2, 3 bonds and a lone pair. Because we have a lone pair adjacent to a pi bond, and we can delocalize that lone pair into our adjacent pi system, this nitrogen prefers to adopt an sp2 hybridization, but this lone pair is delocalized. As a reminder, that lone pair is held in a p orbital, so it can be spread and delocalized across the pi system. This is known as a pyrrole type nitrogen. With that example in mind, I'd like you to take a few moments and approach this next problem. So take a few moments and determine whether each nitrogen lone pair is localized or delocalized, and I'd like you to tell me the hybridization and geometry of each nitrogen atom. So pause the video at this time and we'll discuss this example momentarily. So looking at this first case, we have a nitrogen with 1, 2 bonded atoms and a lone pair and a pi bond. This nitrogen is sp2 hybridized and this lone pair is localized. This nitrogen here has 3 bonded atoms and a lone pair, but that lone pair is adjacent to a pi bond. So this nitrogen adopts an sp2 hybridization, but that lone pair is delocalized. This last nitrogen here contains a lone pair, but no adjacent pi bonds. So this lone pair is localized, and this nitrogen is sp3. For this sp2 nitrogen, it's trigonal planar, the bent variant. This nitrogen, as its sp2, is trigonal planar. This sp3 nitrogen is trigonal pyramidal, as it has 3 bonds and 1 lone pair. So again, we see the effect of localized and delocalized lone pairs on the nitrogen atom's preferred hybridization and thus its preferred geometry. Pretty important in biological settings as the amide bond is actually flat as a consequence of this nitrogen's sp2 hybridization and trigonal planar geometry. Let's look at another case study, in which case we're asked to take a look at resonance stabilization and looking at lone pairs in different conjugated systems. So here we're asked which of the following lone pairs is lower in energy. In general, delocalized lone pairs are lower in energy. As such, if we compare a localized lone pair to a delocalized lone pair, this nitrogen lone pair is going to be lower in energy because it's stabilized via delocalization across the pi system. I'd like you to take a moment and approach these next 2 examples, and I'd like you to tell me which of the following lone pairs in these next 2 examples would be lower in energy. Okay, so again, here we have a localized lone pair versus a delocalized lone pair. The delocalized lone pair is going to be lower in energy. Now, this next case is pretty interesting. Here, both of the lone pairs can be delocalized. However, in this case, for the first structure, we can delocalize our lone pair across multiple atoms. And because we can spread this electron density across more atoms, this top structure's lone pair will be lower in energy. So when a lone pair is conjugated to more atoms participating in a pi system, generally that lone pair is going to be more stable and lower in energy. By the same token, Cations, anions, and pi bonds and lone pairs are stabilized by conjugation. So we can apply the same principle to look at cation stability. So which of the following cations is lower in energy? Well, in this case, looking at these two examples, we have a cation that can be stabilized via delocalization across multiple atoms participating in the pi system, while on the right we have a localized cation. The cation on the left, which is able to be stabilized via distribution across more atoms, is lower in energy and more stable. Looking at this next case, I'd like you to take a few moments and approach this next case, and I'd like you to tell me which cation is lower in energy. So in this case, it's going to be the benzylic cation by far. Why? We can distribute that positive charge across more atoms because each of these atoms in the ring are participating in the pi system. So we can spread that positive charge out across more atoms and in turn stabilize that positive charge. Okay, this concludes the first part of the Chapter 2 lecture, and we'll continue this lecture in the next lecture video.